So now that we have defined what rate law and what power laws look like, which means we have related the rate of reaction to the concentration. So how the rate of one specific reactant depends on the concentrations on how these concentrations vary. What's left to do is basically to relate this concentration to the conversion, and then we're back to the mole balance and design equations for our design of the reactors. So this part of the lecture will be on stoichiometry, which is basically a set of tables that allow us to define concentrations of each species as a function of the conversion. So basically what happens to these concentrations of the reactants and the products as the reaction proceeds, which means as the conversion increases. And in order to do that, we will just go back to our usual reaction. We have AABB goes to CCDD, and basically from that, we said that we take our limiting reactant as basis for our calculations. So in this case, if it's A, then we can relate the rates of the reactions, rate of reaction for each species based on this equation that we saw earlier. So basically we can see that we have rate of A divided by A, its coefficient is equal to rate of B divided by its coefficient, and so on. And yeah, and as mentioned, we use the limiting reactant as a base for the calculation. The reactant that dissipates or disappears first, or the reactant that we don't have enough of at some point. So from our definition of conversion, at any given time, the moles of A in a batch reactor, for example, that remain are basically the rate of A that the moles of A that we initially put minus the moles of A initially put times the conversion. So this is basically our definition of conversion from the first lecture. And if you can do the same for the moles of B, and that comes in handy the way that we relate the rates of reaction to each other. This is just putting together moles of B reacted, which is basically moles of B reacted divided by moles of A reacted times moles of A reacted. And we already know this, we can define that from our conversion. So that's just multiplication of the conversion, and these rates are just the ratio of the two coefficients, so B divided by A. So moles of B reacted are B divided by A times moles of A reacted. This is the change that happens in terms of B in the reaction. So if we check what moles will be remaining in the reactor after this B is reacted, we will have basically, we'll just subtract this from our initial moles of B. And we can do that for all the reactants. And that starts basically our building of the table. In fact, if we see here, we have all the species on the first column. Initially, we have all these concentrations in the reactor, and then they change in terms of now, to make it easier for our calculations, we express all of them in terms of the initial moles of A. And this is what it looks like. This is the change in A, so A reacted, B reacted, C reacted, and D reacted. or in a way, A disappeared, B disappeared, C formed, and D formed. And what remains in the reactor is then what we have initially in the reactor for each of the species, and then minus in the case of disappearance and plus in the case of formation, and then we have the moles of each species in the reactor at a given time. And we can just add this, and then our total reactant count will be n tot plus, you can see we just add the coefficients together and then NaOx, because that was why we were basically expressing everything in terms of the initial moles of A. And this term here is, we call it delta. It appears in many of the tables, so it's nice to have it just as delta. And yeah, so we call that one a delta. It's just the change basically between the total moles reacted within the whole reactor system as a function of R divided by the moles of A reacted. So it's a ratio between the total moles of the reacted, so considering B, C, D, and all, per unit of moles of A reacted. And the concentration of A is just the number of moles of A per unit volume, so it's Na per V, and this is at any given time. And therefore, based on the definition of the conversion, we can just express it as a function of the initial moles of A divided by volume. We can do the same for B. The concentration of B are basically moles of B per unit volume. And similarly, we can express that as a function of conversion. And the way we do that is just we use the table. So these are the moles of B at any given time, which is the initial moles of B minus the change in B. And then we have the volume. Then if we basically take out the initial moles of A and AO out of this equation, then we get basically this ratio, which is the ratio of the mole fractions in the beginning. We call that delta, and then we have the concentration of B as a function of the initial moles of A. But obviously we will need the volume as a function of conversion in the case of a variable volume system. If it's a batch, then we will just call this V, because it will be the same as with the with time. But if we have changed, then we will need to define the volume as a function of conversion. So for constant volume batch reactors, then the total volume is equal to the initial volume, so we'll just keep that. And the concentration is therefore will be in relation to the initial volume, and our concentration at any given time for a species A will be basically the initial concentration times 1 minus x, or 1 minus the conversion. For B, we can do the same. In this case, we're talking about a batch, so we still keep the initial volume. So it's not a function of volume. The volume is not a function of the conversion. And then we just take our initial concentration of A, and then theta B, which we said is the ratio between the initial moles of B divided by the initial moles of A, and then we have the change in B as a function of conversion, and therefore it will also be a function of the concentration of A in the beginning. So this way we also have related the concentration of B to concentration of A. The idea here is to express everything as a concentration of A and conversion. So concentration of A is a function of A and concentration of B is a function of concentration initial of A and conversion. And then we have the rate law for the reaction. The rate of disappearance of A is a rate constant A times Ca Cb, and if we express Cb in terms of CaO, we can just replace Ca and Cb here, and then we have basically this function here, which basically relates our rate of reaction in terms of conversion, and then the initial flows into the system. So these are all known parameters, basically, because the concentrations are the ones that we monitor, and especially the initial one is what we already have. So if everything depends on that, then it makes things much easier. And then by substituting, therefore, these parameters that are known, we can basically size our CSTR and PFR using a Levenspiel plot or just by calculating our the volume of the reactors. As you can see here, we basically just did the rate of reaction for a batch this way, related it to conversion, and we're saying that we can, with that, construct a design of the volume of CSTR or PFR. So we can, since the rate of reaction is not a function of the reactor, but just a function of the concentration and the the properties of the reacting materials, then whatever rate of reaction that we get here, it will be the same also for CSTRs and PFRs. This is given the condition that we have a constant volume also in the CSTRs and PFRs. If changes happen in the volume of the reactants and products in the system, then if the volume of the system changes, then things will change. So, but we have other expressions for that we will get into now. In the case of flow, basically we use the same expressions. We have the species, we have the feed into the reactor, and then we have change into the reactor in terms of the initial flows of A. And then we have what goes out of the reactor. So in terms of also the initial flow of A. And similarly, we have the delta, which is, as we said, the ratio between the total moles reacted in the system per unit of moles of A reacted. And then we can express that also this way. So the total flow out of the system is equal to the initial flow plus delta times initial flow of A times the conversion. And in the case of when we have a change in volume, then we will need to use the ideal gas law to account for the change in volume. And therefore we will use the moral flow at different concentrations, and then we will change the temperature and pressure based on how the reaction progresses. But here you can see how the concentration is defined in terms of the initial concentration of A, and then all the changes in pressure and temperature that will cause the change in volume in the system. And we can see that for each and every species. And eta here in these expressions is basically the initial mole fraction of A times the delta, which we said is the moles of the total moles reacted per unit of A reacted. Okay, so basically now we know how to construct tables and how to relate the different concentrations with the conversions. And if we put this together with the rate laws, then we have basically the rate of reaction as a function of conversions, which is what we needed to design a reactor. And therefore, this is a very nice algorithm for designing a reactor. So basically, our main equation is the mole balance equation. That is where we start always. So we define the mole balance, we decide what reactor we are talking about. So then we basically apply it to each and every type of reactor. So if we're talking about batch, then we have this expression for the time that it takes for the reactions to take place. And then for CSTR, we have this algebraic function, and then and so forth. So basically we have the mole balance. We make the design equation by making this mole balance specific to our reactor of interest. And if we are given the rate of reaction as a function of conversion from the lab or somewhere, then we can just use the Levenspiel plot or just calculate our design parameter, whether it's volume or time, and we have finished the design of our reactor. But if we are not given the rate of reaction as a function of conversion, then we need to find that. In order to find that, basically what we do is we go to the rate laws, and the rate laws are determined either through power law, or we apply that to the specific reaction type that we're dealing with, whether it is reversible or irreversible reaction. And then once we have this rate of reaction as a function of concentration, then we can use the stoichiometric tables to relate the concentrations to the conversion. And once we have done that by combining the rate law with the stoichiometries, we get the rate of reaction as a function of x, which is exactly what we would have gotten from a lab, or what we would have assumed as a given in the previous lecture. And once we have that, we're left but just applying this rate of reaction as a function of conversion into the design equations, and we have our design this way as well. Yeah, that was it for this lecture.